Thanks for the organizers for inviting me to deliver two lectures actually on fundamentals of magnetism. I feel privileged to be the instructor of this very prestigious magnetic summer school and to have the great opportunities to interact with not only the students from the world, but also the experts, local experts here. Since I will be the very first speaker for the entire summer school, my lectures will be dedicated to the fundamentals and basic knowledges of the subject. So I will be trying to, keep my lectures general, without dragging too much into the technical details. But still, just in case there are anything that you feel puzzled, just please feel free to raise your hand and interrupt me during the lecture. Okay. I will basically, split my lectures into two parts. The first lecture will be basically delivered by playing the slides, and the second lecture will be basically given by board writing. So the first lecture focuses on the statical properties, namely how magnetism and magnetic structures are being formed as a competition among different energies and interactions. Well, the second part of my lecture will be, we'll shift the gear and focus on the dynamical properties, namely how a magnetic structure and ordering react to external stimuli, including magnetic and electrical stimuli. Okay? So here's a roadmap of the first part of my lecture concerning the statical properties. So let us start with, the very basic concepts. The building blocks of magnetic materials are the magnetic moments. So at a microscopic level, the fundamental building blocks of any magnetic phenomena is the magnetic moment. So historically, the magnetic moments were once, pictured under a wrong physical picture, namely the magnetic dipole, which was analogous to an electric dipole consisting of a pair of oppositely charged particles. But before long, this picture was proven to be wrong, as Ampere proposed a different microscopic picture where the magnetic moments are not associated with magnetic charges. And nowadays we know that magnetic charges simply do not exist, but instead magnetic moments arise from the persistent circulating current known as Ampere's current. So there are numerous, microscopic current loops in our materials, and the current there were persistent and never stop. And it is the motion of the charges in the form of microscopic loops that gave rise to the magnetic moments. So this was the Ampere's picture. But at that time, Ampere were not able to explain why those currents are simply persistent and never stop. And it was, only after the advent of quantum mechanics that people, were able to fully understand why the currents are persistent. Okay. But anyhow, from a fundamental perspective, there are two, basic differences, distinguishing the two pictures. So in the wrong picture, in the magnetic dipole picture, the magnetic field lines stems out of the positively charged magnetic particles and ends on negative particles. While in the current loop picture, the magnetic field lines never ends. So they simply form all closed loops. So even from afar, the two pictures do not give practically different predictions from afar. They both look pretty much the same, but microscopically, the divergence of the magnetic field in the correct picture is zero, and is always zero. And we know this is consistent with the Maxwell's equation. And another fundamental difference between the two pictures is that in the Ampere's picture, the magnetic moments are intrinsically associated with an angular momentum, because it arises from the circular motion of charged particles. And historically, the first unambiguous experimental justification of the correct picture and the falsification of the wrong picture was attributed to what we nowadays known as the Einstein-de Haas effect. Okay, the Einstein-de Haas effect. The experimental setup is pretty simple. You simply, generates a static magnetic field by the solenoid to polarize a paramagnetic materials such that there are lots of magnetic moments will suddenly be polarized inside the material, creating a finite angular momentum, finite magnetization in the system. So then what was observed is that during the magnetization process, the paramagnetic material slightly rotated, which directly indicates that angular momenta were transferred from the spin or magnetic degree of freedom to the mechanical rotation, which unambiguously justifies the Ampere's picture that magnetic moments are indeed associated with angular momenta. Okay, so this was known as the Einstein-de Haas effect. And by the way, I think in the same year or the following year, the reverse effect of Einstein-de Haas, carried out by Bernoulli, also just by the reverse process. So if you rotate a paramagnetic material to give it a fairly large mechanical angular momentum, then the material will be slightly polarized magnetically. So the Einstein-de Haas and the Bernoulli effect as a reciprocal effect, they justified the Ampere's picture. So this was, the static property, and the difference between the two pictures also directly manifest in the dynamical effect. So here, what is illustrated here is a comparison between electric dipoles P and magnetic dipoles. The magnetic or current loops, whatever. So it's the magnetic moment mu. So even though the energy form between electric and magnetic dipoles are pretty much the same, just the vector dotted product with the associated field. But when you push away, the moments away from the energy minimum, then the way that they react to this perturbation is fundamentally different. While the electric dipole moments simply oscillates back and forth in the plane, the magnetic moments will become oscillating around the magnetic field. Okay, and it's rotating in a right-hand way, which we'll revisit in the second part of this talk. So the precessional motion of the magnetic moments about the applied magnetic field has a frequency determined by a physical constant known as gyromagnetic ratio gamma. So this was the dynamical meaning of the gyromagnetic ratio, but historically the gyromagnetic ratio was defined as the proportionality constant between the magnetic moments and angular momentum. So we just emphasize that the two quantities are mutually proportional. So for a negatively charged particle, such as the electrons, the mechanical angular momentum is pointing in the opposite direction as the magnetic moments because of the negative charge. Well, for the positively charged particles, such as the a nucleus, then the mechanical angular momentum and the magnetic moments are in the same direction. So the take-home message here is that for electrons, which consists of the most common cases of magnetic moments, the two quantities differ by a minus sign, and the minus sign sometimes is absorbed by the definition of the gyromagnetic ratio. Okay. So here, using a heuristic yet non-reverse picture, we could somehow, quantify the gyromagnetic ratio, the constant between magnetic moments and angular momentum. So for example, if we assume that a charged particles is moving on a tiny loop, then the effective current associated with this circulating motion is simply the charge, either positive or negative, divided by the period of oscillation, the cyclotron motion. And then the magnetic moment is simply the area of the loop times the current, okay? So, like I said, this is a non-rigorous but heuristic picture that captures the essential physical, basis of magnetic moments. So, in that way, we can write down the gyromagnetic ratio for electrons as the ratio of the electron charge over the electron mass. Okay. So this is the gyromagnetic ratio, and the same expression is obtained for positively charged particles, for example, the nucleus. And because nuclei are positively charged, so the gyromagnetic ratio also differ by a minus sign. So other than the sign, the absolute value of the gyromagnetic ratio associated with the nucleus is also orders of magnitude smaller than the gyromagnetic ratio for electrons, simply because the nucleus have a much larger mass, even though they carry similar charges, but the mass are so off from each other. So in the following of this lecture, we will simply focus on the magnetic moments associated with electrons or negatively charged particles. Okay? And quantum mechanically, we know that angular momentum should be quantized in terms of h bar. So if we simply represent the quantum number of the mechanical angular momentum by a vector, or more specifically, an integer valued vector, then the HL denotes the quanta of the angular momentum, so times the gyromagnetic ratio that produces the magnetic moments. So from this relation, then we immediately infer that the smallest possible value of a magnetic moments in nature is where the quantum number is said to be 1. So 1 is the lowest meaningful quantum number. Well, 0 means nothing. 1 means the minimum. So that defines a fundamental physical quantity known as a Bohr magneton. Okay, so a Bohr magneton is the smallest possible magnetic moments that an electron could possibly carry concerning quantum mechanical effects. And in standard international units, this is represented here. It could be either written as Joule per Tesla or electron volts per Tesla. So, and the dimension of the magnetic moment, so is the Bohr magneton, could also be represented in electromagnetic units as ampere times meter squared. Okay, ampere times meter squared. So with the physical dimension of magnetic moments and the fundamental, the smallest possible moments, then we are able to define the central quantity throughout my lecture, or I think it's throughout the school, is called the magnetization. The magnetization is physically defined as the volume density of magnetic moments. The volume density of magnetic moments. So you could simply take a volume average of numerous magnetic moments and define the local magnetization as the volume density of moments. So then the magnetization, it comes with a physical dimension of ampere per meter, because you divide this guy by a volume. Okay? And so I will just quickly give you an example. In transition metal elements, in transition metals such as iron, nickel, and cobalt, the typical value of the magnetization at low temperatures is on the order of 10 to the 5th to 10 to the 6th ampere per meter, okay, the volume density of moments. So, okay, so thermodynamically, the magnetization is defined as the change of the magnetic free energy with respect to the magnetic field. Okay, so this is the thermodynamic relation for magnetization, and so this relation directly tells us one fact. So in order to have a non-zero magnetization, the free energy should explicitly depend on the magnetic field. And you may think that this is just pretty straightforward, but unfortunately, within classical electromagnetics, this is not true. Because using a pure classical picture, the magnetic field never does work on any charged particles, because the Lorentz force is always perpendicular to the instantaneous velocity, which is only able to change the direction of the motion, but does not change the value of the kinetic energy of charged particles. Therefore, by applying a magnetic field within the classical picture, by the way, I emphasize that, then the magnetic field does not change the energy of the system. Therefore, the free energy does not directly depend on the magnetic field, so which always gives you a zero magnetization. So this is known as the Bohr-van Leeuwen theorem, which simply says that no magnetization in classical physics. Okay. Well, you know, we could spend like half an hour proving this theorem, but for the moment, let me just skip the reverse proof. But the essential idea behind this theorem, I mean, in justification of the theorem is, you know, using classical statistics, then, you know, the partition function is independent of the magnetic field because the field dependence could always be gauged away by a proper coordinate transformation. That transformation, removing the impact of the magnetic field, always exists. Okay, so this is a non-reverse but heuristic proof, if we could call it a proof. Okay. All right, so no magnetization within classical physics. Then, in order to, you know, study magnetic phenomena, we have to resort to quantum mechanics. So, under a quantum mechanical picture, every physical quantity becomes an operator, including the angular momentum. Okay, we know the magnetic moments arises from angular momentum of charged particles. So angular momentum got quantized and becomes an operator. So what is shown here, this is the this is known as the orbital angular momentum operator, and it satisfies a commutation relation. This is, let me use the laser pointer. So it satisfies the commutation relation. It is a matrix relation. And a quantum state of a magnetic particle, you know, should be characterized by, you know, two distinct quantum numbers. One is the total angular momentum quantum operator, and this associated quantum number is denoted as L, and the other one is called the magnetic quantum number, which has the physical meaning of the projection of the total angular momentum on the quantization axis. The quantization axis has to be prescribed, and this is the projection. So in quantum mechanics, we know that the angular momentum should always take the natural numbers, the integer numbers, each of which corresponds to a specific atomic orbital. And once the arrow is chosen, then the magnetic quantum number, or the projection, can only take the quantum values all the way from minus arrow to the positive arrow. So what is shown here, illustrated here, is the arrow equal to 2. So we have 5 choices for the magnetic quantum number: -2, -1, 0, 1, and 2. Okay, so nowhere between the allowed quantum number is allowed, because we are now under a full quantum picture. Okay, so under a quantum picture, the choices of angular momentum becomes quantized. So is its projection onto the quantization axis. But the complication comes from another quantity called the spin of the electron. So besides the orbital motion of electrons, which gives rise to the orbital angular momentum and orbital magnetization, there's also a quantum property called the spin, or the spinning motion, which is the intrinsic and fully quantum, which has no classical correspondence. So the spin angular momentum, independent from the orbital degree of freedom, can only take half integer values. And for a half integer spin, the projection onto the quantization axis can only be positive or negative 1/2. And similar to the arrow and M arrow, then we also have the S and MS for the spins. So at this moment, then we have a complicated situation. What if we have both arrow and S? What if both the orbital and the spin angular momenta exist? Okay. So if the two degrees of freedom are decoupled, then we can simply add them up, and this is a trivial. But the thing is, for most of the cases, we have to care about the intrinsic coupling between the orbital and the spin degree of freedom, known as spin-orbit coupling, which is a relativistic correction to quantum mechanics. Okay, so this is a combined effect of quantum and relativity. So the spin-orbit coupling. So in the presence of the spin-orbit coupling, the orbital and the spin angular momenta no longer separately conserved. They no longer separately conserved, but their vector sum, denoted as J, which is the total angular momentum, is still conserved, even in the presence of spin-orbit coupling. Okay. Therefore, by considering spin-orbit coupling, then the good quantum numbers, I mean the eigenvalues, are no longer the arrow and S individually, but it should be replaced by the total angular momentum J and the projection of J on the quantization axis, which is Jz, and the relative contributions from orbital and spin. So we have 4 independent quantum numbers to properly characterize a complicated quantum state in the presence of spin-orbit coupling. So this is the parameterization of the wave function. Okay? Total angular momentum, its projection on the quantization axis, and the arrow and S, the participating components. Okay, 4 quantum numbers. All right. However, now, once we take into account both the orbital and the spin angular momenta, we also have another complication, because the gyromagnetic ratio associated with the orbital and the spin degree of freedom, when we convert them into magnetic moments, are different. The conversion factor for the orbital is 1, while that for the spin is 2. So then, what is the big deal about this difference? What is the direct consequence of the different proportionality? So here, this is an illustration of the vector sum of the angular momentum. So we simply add up arrow and S to produce the total angular momentum J, no problem. However, with this 1 and 2 difference, the magnetic moments are pointing in a different direction, because I have to double the strength of the arrow in order to draw the total moment. So here, the green arrow represents the total magnetic moment, while the black arrow represents the total angular momentum, and they are not even collinear. Then we have a problem. So that indicates that these two quantities, the total moments and total angular momenta, they are not simply proportional to each other, like arrow and S, because of this factor difference. However, if we can heuristically view the picture as a quantum precession of the total moment around the total angular momentum, then we can still take the time average of the total moments, or let's say it's simple the projection of the total moments on the quantization axis. And now this is indeed collinear and proportional to the total angular momentum. So this kind of construction, based on the effective picture, and this gives us an effective gyromagnetic ratio. Let me answer that. This is effective gyromagnetic ratio between the total angular momentum and the projection, or the time average of the total moments. Okay, only after taking the average or projection do they become collinear. So if we factorize out a fundamental Bohr magneton, their proportionality constant is known as the Landau G factor. So the Landau G factor for the spin is simply 2, for orbital is simply 1, but in general, this depends on both S and L. And you could easily verify that when L is 0, this reduces to 2. It reproduces the spin limit. When S is 0, while keeping L, where J is equal to L, then the Landau G factor simply reduces to 1. So it interpolates between the 1 and the 2. But this is an oversimplified picture because in real materials, the Landau G factor is not simply somewhere between 1 and a 2. It could be even 5 or 6 or even 10 in the most extreme cases. That is because the S and L may not be collinear with each other. They could either be constructively add up or destructively add up, making the effective G factor very case dependent. Okay, the Landau G factor. All right, so this is concerns about one electron. So one electron carrying L and S, and the superimpose in a complicated way, very case dependent. But what if we have an ensemble of electrons, multiple electrons? In that case, we have to properly take care of the individual contributions from each electron, and each electron contributes an S and L. So in what is known as the LS coupling, we should simply add up the individual orbitals from all electrons together to define a total orbital angular momentum L, and in the same way we have in the total spin angular momentum. And then after this summation over each individual electrons, then we can apply this picture to the total L and the total S. So if that is the case, this is known as the LS coupling. But there's a caveat. The LS coupling is only applicable when the crystal environment is relatively weak. At least it's much weaker than the spin-orbit coupling. So once again, the spin-orbit coupling dominates the crystal field or crystal environment, is the necessary condition for the LS coupling to be applicable. But what if the opposite case is true? What if the spin-orbit coupling is smaller than the crystal field? Well, in that case, we could still have the LS coupling. However, the empirical rules associated with the LS coupling, which is known as the Hans rule, becomes invalid, or at least it becomes questionable. So here, let me explain with some detail. So the Hans rule is only an empirical rules, accompanying the LS coupling, assuming a fairly, strong Coulomb interaction, a fairly weak crystal field. So the Hans rule is summarized in decreasing order of priority by as follows. So you should first maximize the total S, and then if this is already satisfied, then you're going to maximize the total L, and then depending on whether an atom is Oh yeah, I will just try to give you a picture on the next slide. So the crystal field, the Hans rule and those simple oversimplified pictures, are borrowed from the atomic physics, which concerns with, essentially one atom, where the Coulomb field from the nucleus is spherically symmetric. But when you place an atom in a crystal environment, then the environment is no longer spherically symmetric.
So the crystal field is that electrostatic field from other near...
Yeah, from neighboring atoms. And maybe I could play this slide here. So those are illustrated two typical crystal environments, the octahedral and tetrahedral environment. So when the crystal field becomes substantial, then we can no longer ignore the presence of neighboring atoms and adopting an oversimplified atomic picture. So this is also where the Hans rule as an empirical rule breaks. It becomes invalid. So, well, the study of the crystal field, that is a separate topic. And unfortunately, we do not have enough time to delve into the topic of a crystal field, but a really quick and really general picture is that once the crystal field is taken into account, then the atomic orbitals for single atoms, which were constructed by spherical harmonics, are no longer the eigenstates. Rather, it is their linear superposition that are the true eigenstates, which is split into two groups, known as the EG orbitals and T2G orbitals. But it's a complicated business as to which group has a lower energy. That depends. So once the crystal field environment is being taken into account, then the simple picture, like I said, is invalid, and that's where the sophisticated numerical techniques are needed. Okay. But I mean, on a general level, there is a very profound implication of the crystal field if that dominates the spin-orbit coupling. And this is known as the orbital quenching effect. So once the spherical harmonics, satisfying the high symmetry, makes the linear superposition into EG and the T2G orbitals, then the orbital wave functions becomes a pure real wave functions. It no longer carries an exponential factor depending on the azimuthal angle. And the direct consequence of that is the quantum average value of the orbital angular momentum vanishes identically. So this physically represents the complete suppression of the orbital angular momentum by the crystal field. This is known as orbital quenching. In real materials, which could be complicated, then we could, for example, have a partial quenching. It's not a complete suppression, it's only a partial suppression. Okay, so any questions so far? Mm-hmm.
I just downloaded these slides, but this exactly is not on the recent version.
Yeah, I added this slide this morning, and I will upload my record.
Okay.
No worries. Any other questions? Mm-hmm.
Also, you just explained that, but Hans.
Oh, you may.
Okay, so I think if I got it right, that you explained that the Hans rule becomes invalid when the crystal field becomes stronger. Am I correct? So if Hans rule is an empirical rule, so it has been empirically. It's not like it comes from a theory. The data has been collected and empirically it has been formulated.
It has been formulated under the context of atomic physics. It's not the solid. We are talking about the solid state magnetism.
So the Hans rule, the empirical rule, was formulated from atomic physics,
Yes.
considering just maybe a single electron.
Or independent nearly independent atoms.
So like gaseous state.
Yeah, for example, very dilute quantum gas, for example. Yeah.
Oh, okay.
Yeah.
Understood. Thank you very much.
Thanks for the good question. So here is a subtle point. So the atomic environment and solid state environment are fundamentally different. And here in our context, the difference manifests as the crystal field. But there is, certainly other implications. For example, the Bloch theorem, right, for the electrons. Yeah, just to give an example.
Thank you.
And by the way, that's why solid state physics and atomic physics are different fields. Okay. All right. So now let's move on to the next topic. So now we have a quantum picture of the physical origin of magnetic moments. Now the next topic is how do the magnetization or magnetic moments react to the application of a magnetic field? So once we apply a magnetic field, we could induce a magnetization in an otherwise non-magnetic material. So, and the ability of magnetic polarization is characterized by the physical quantity known as the magnetic susceptibility. So in the linear response region, which basically says the magnetic field goes to 0, then you could define the magnetic susceptibility in two ways. Okay? But regularly speaking, for high field, these two definitions are no longer equivalent. But now, in a simple picture, we simply treat them as equivalent. So here, I mean, there's also a subtle point. Somewhere in the literature, people define the magnetic susceptibility in terms of the H field. And somewhere else, they use the B field, which is the magnetic induction or magnetic flux density. But in electromagnetism, we know that H and the B are simply differ by a constant, mu0, the permeability. Okay? So here, practically, we do not just be bothered with this subtle difference. We just use them interchangeably. Just be borne in mind of the magnetic permeability. All right? So thermodynamically, because the magnetization is the derivative of the free energy with respect to the field, as we commented on the Borel-van Leeuwen theorem, then the magnetic susceptibility is the second order derivative of the free energy with respect to the field, preferably with a given temperature. Then, if we plot the magnetization versus the applied magnetic field inducing the magnetization, then we can classify, based on the sign of the magnetic susceptibility, the following three cases. The first case is known as diamagnetism, which basically means that if you apply the B field in one direction, you induce a magnetization pointing in the opposite direction. It goes against the applied field. This is known as diamagnetism. And the other case, which is more common, is called the paramagnetism, which means you apply a field, you simply induce the magnetization in the same direction. But the total number of magnetic moments in the material is limited, is finite. So eventually, the magnetization could not be just growing indefinitely. It will eventually saturate, okay, once you have polarized all magnetic moments in the material. So this behavior is known as the paramagnetic behavior, the paramagnetism. So for small field, the magnetization increases linearly, almost linearly with the field, until eventually it bends down towards a saturation. And there is a negative and a positive saturation. So the paramagnetism. And yet another type of behavior is the ferromagnetism, which basically opens the MB curve